Oswald giving us current and futures for Open Daylight.
Cool. Okay, thanks. Matt and I are going to tag team this a little bit. This is kind of an update from the one we did a couple times back, so I'll just give you a little idea of what Open Daylight is. By the way, how many people know what Open Daylight is? A little bit. Okay. So, and we'll try to make this fast. So, what is hydrogen? We named the releases all by the elements. We did a doodle poll. This is what the people wanted to have. So that's what we did. I'll give you a little bit of what's gone on, and then Matt will pick it up and take the rest of it. So, what is Open Daylight? This is kind of the canonical slide. It's an open source project to build sort of an SDN platform. It's housed under the Linux Foundation. They give us all of the sort of marketing, IT, and all of that kind of support. The goal is to create a piece of code or a bunch of code that is basically open source and covers the major pieces of some kind of SDN solution. And we really want to have it adopted by the industry. An example of something like this would be like Open vSwitch. People build that into their products. They can pick it up as open source and other things like that. So we want vendors to use it too. And one of the things I learned over the year or so that I've been involved with this is that the community aspect of it is most important. So you can slap some kind of open source language, a license on your code, put it up on GitHub, but that's not going to make it open source. Nominally. But the real power of it is in the community. So what are we building? Well, it's a community, as I said, that's the main thing, but an evolvable SDN platform. So contrast that with like a controller, right? We want this thing to be able to be very configurable, very modular. Common abstractions for northbound APIs, people have to be able to write to stable APIs. Whatever we need in the middle to connect that to the southbound and programmable services that are underneath it. And then, of course, you need applications that run on the thing to make it useful. And glue of all different kinds to make it work, including engineering systems. So this is things like tool chains, how you do collaboration, all of that kind of stuff. So here's what it looks like. This is kind of the scope of the thing. In the middle, there's kind of this controller platform I was telling you about. Oh, I got to watch the time here. On the south side of it, there's plugins. So protocols are pluggable on the south side. And on the north side, there's REST APIs, not surprisingly. You can also write to the Java APIs here on the north side of it if you need to for performance issues usually. Who's in it? Well, you know, everybody, or at least most of the vendors are in it. There's kind of 3 membership levels, and I'll talk about this, but basically, you don't need to be a member to either get the code or contribute. You can actually even get on the technical steering committee or even on the board without being a member. But platinum membership comes with some board seats and things like that, and then gold and silver have their own things. But so there's quite a few of familiar names involved. So what did we do? We've been working on this for about a year, a little more than a year. And Open Daylight is really multi-project. So we tried to bring all the projects that wanted to together into what's called a simultaneous release, kind of a common thing in the open source world. And as I mentioned, we named it Hydrogen, and we planned to release it last December. That was our plan. And we kind of grouped up the functionality together and kind of had what were basically editions. There's a base edition, which, what you can think of as, it was like an OpenFlow controller. There was a virtualization edition because there were parts from virtualization functionality in there, and then there was a service provider edition. I'll show you what those all are, although I have to go faster. Here's the simultaneous release plan. All of these, I'm just showing you this. You don't have to read it. I'm just showing you this because these open source projects all have a plan that looks like this. There's milestones, then there's release candidates, and then you try to get the thing out. Well, it didn't really get there. We kind of got around, we got around to releasing it around February. These were the projects that were in it. As you can see, there's a whole bunch of different things. I'll just mention right here that for the service provider edition, what was in there were things like BGP-LS and PSUP, because it was kind of thought that, okay, that's traffic engineering, and then a lot of other things, and I'll show you how we grouped that together, but that was one of the main things that was in there. We did OpenStack integration. This is a picture of it so you can see how it works. It basically, the OpenStack integration was basically a pass-through of the Neutron API into Open Daylight, which basically pushed all the complexity into Open Daylight. The design of Neutron is sort of in flux right now, how much smarts should be in there. Okay, so that's a long story there. Okay, I'll keep going then. Here's the helium thing. I just put up the periodic table because the first thing was hydrogen, obviously the next one's going to be helium, and so forth. Again, a release plan that looks like the last one. The reason that we have this is because we want to get on a deterministic cadence, so you'll get a new release of this every 6 months, basically, and it'll go helium, lithium, and so forth. What's in helium? Just tons of stuff, including all of this policy stuff, some packet cable stuff, which was kind of interesting. I'll just pick out one here for you. TTPs are table typing patterns, which were intended to restrict the OpenFlow 1.3 spec enough so you could actually implement it on real hardware, and all kinds of other things. So there'll be a lot of interesting stuff in helium. Okay, so here's a brief note on the project lifecycle. So the project lifecycle, these things all have project lifecycles, right? And just like you would have in any other software. But the key thing here, and this is what I want you to look at, is what I highlighted here, was that you don't have to be a member to bring a project into Open Daylight. It's an open source project. Anybody can do it. So, and we've had it. A lot of the projects that were in hydrogen were actually brought by non-members. Okay, so now it's your turn, I think. I'll just talk about this. So the thing about lithium is, okay, that we're trying to get now 2 releases ahead, and we're just trying to get this to be very deterministic, and that's good for the consumers, and it's also good for the developers because they need to know when they need to hit these milestones in order to get into these releases. So it's a little bit too early for projects for lithium because that's 1 release ahead, but we already built this, right? So this should look familiar to everybody after the first 2. It's the same, just shifted in time by 6 months. Okay, now. Here's the next one.
Yeah. Hello. My name is Matt Oswalt, and I just wanted to really briefly sum up sort of my experience in this. And we had, as Dave mentioned, we had a release in February of hydrogen for Open Daylight, and we had a summit that sort of wrapped up that release in Santa Clara, I believe it was. And one of my favorite quotes from that was Open Daylight isn't just for developers, and I think that's one of the biggest key points for me specifically, and for a lot of folks that I work with, because the general idea that I try to communicate to folks that want to get involved is that you don't really have to know code to be involved with this community. Dave really he hit on a great point with this concept, is that community is huge with the Open Daylight project. One of the ways that we try to how do you oh, there we go. Yeah. One of the ways that I try to illustrate this point is I did a talk recently on this, and what I want to illustrate with the concept of network programmability is that one of the most fundamental things that you can use in a lot of the SDN talks that you probably hear about is that programmability is awesome, but ultimately you're still going to depend on a lot of the standard protocols that we use on a day-to-day basis. And I try to hammer this home with both developers and network folks, because ultimately that's going to be the biggest key in understanding this. So with respect to Open Daylight, one of the best things that you can do to get involved as just networking professionals like myself is one of the use cases is a sanity check for matching on protocols. We've had a lot of talks recently, specifically with matching flow state. If you have, for instance, you're matching on an ether type, and that ether type says that the packet is IPv4. However, the packet isn't IPv4; it's IPv6. I mean, it's silly stuff like that. You'd be surprised how useful that kind of knowledge is. Maybe more specific. You're matching on IPv6 neighbor discovery packets, but the address doesn't match the format that it's supposed to. That kind of knowledge is actually really, really valuable in this community. And there's many, many use cases where somebody could sit down and just look at a list of features that have been added recently and just do that sanity check and make sure that they match exactly what they're supposed to be doing from a protocol perspective. One We're also implementing a lot of standards in code. As Dave pointed out, we've got a lot of projects that implement various protocols and libraries that just simply don't exist yet in the open source world, or at least not in this modular fashion. So another thing that's useful is being able to test and integrate a lot of these projects with existing gear and existing software, software that we're used to using every day. So in summary, this is, in my opinion, one of the best communities that that exists out there to chase that pyramid that I illustrated, and basically enforcing that idea that network fundamentals are still just that, fundamentals. And they're going to be the key resource in doing all of the stuff that we've been talking about. I'm on Twitter. Most of the folks in the community are on Twitter, but IRC is probably the best place to reach everybody in this community. Hashtag OpenDaylight on Freenode. There's many other sub-channels, but the wiki has all of those. Hashtag OpenDaylight is definitely the best place to start. And with that, I think we're finished.
Okay. I guess we can take a question or two, if anybody has one, after that whirlwind tour. Okay, well, thanks a lot. And again, please get involved if you have the time and energy.
And next will be Clarence Fizz from Cisco, presenting how to use segment routing for egress peer engineering.
Thank you. Good afternoon. So the context of the talk is segment routing. I introduced that technology a year ago at NANOG. The implementation is now available in iOS XR 5.2.0. We committed to efficient standardization. 15 drafts are published, and we managed to get the cooperation of all the key vendors who co-signed the protocol extension draft, as we committed to the lead operators. Lead operators, significant group, so we have a significant industry support, many committed deployments, many use cases. And if you want to have more information, please consult that public website. The focus of the use case we want to look at today is EPE, egress peer engineering. The details are in these two IETF drafts that we published with colleagues from Facebook and Yandex. Daniel Ginsberg from Yandex presented EPE last week at NANOG, and the link to the presentation is also available on the presentation and on the public website. So this is the reference diagram for this use case. We are in the red AS number 1. We are looking at a destination M/8, which is on the far right in the black AS number 4. And we have two transit providers to reach this, the green AS2 and the blue AS3. We have multiple border routers that are connected in different ways to these transit providers. In yellow, we display the BGP best path from AS1 viewpoint to the destination M/8, which is B. We use segment routing within AS1. We have no dependency on what the transit providers do. It's only based on policy within AS1. The node seat for C is 64. This is the global label within AS1 that gives the shortest path ECMP aware to C. What is the goal of that use case? I'm sorry. In green, the green arrow shows the typical path that will be followed from AS1 to M/8. It will follow the best path according to BGP, the border router B in yellow. What we want to achieve through the use case is to allow a controller to traffic engineer on a per flow basis traffic to M/8 via other border routers, C for example, and specific peering links to these transit providers. So for example, the traffic from A to M/8 would be directed via C instead of B, and then use the green transit providers, while the traffic from a host H within AS1 is directed to M/8 via another border router than the best path, so C in this example, and via a different peering link and transit AS, for example, the blue AS and the peer number E. So that's the goal, and one constraint we want to put is that this traffic engineering policy must be programmed by injecting state only at the ingress border router or at the source content host. So the per flow state is only at the ingress border router or at the host. Nowhere else in the network. How do we realize this? Let's zoom into the eBGP peering topology of C. We have a single hop eBGP session to D, we have a single hop eBGP session to E, and we have in dashed a multi-hop eBGP session to F. That multi-hop eBGP session recurs over two physical interfaces from C to F. What the EPE functionality on the node C does is that it automatically allocates a local label for each peer. For example, a label to D, a label to E, and a label to F. We call these BGP peering segments and specifically peer node segment. They are allocated to each node. And they would give ECMP if in the case of F, you have multiple physical interfaces to that peer. For multi-hop peer, like F, we also allocate a peer hatch segment, a local label for each physical interface to the multi-hop peer. This allows you to traffic engineer either on a per peer basis or on a per physical interface to the peer. Once the local label allocation is done, C exports the topology, the external topology it has to his peers, together with the related labels to the controller. And this is a simple, straightforward BGP-LS extension. Why? Because we want to distribute the external topology together with the labels that are associated and the hierarchical dependency between the peer hatch and the peer node segments. The controller receives the BGP-LS feed that describes the internal topology, this is classic BGP-LS, plus the BGP-LS EP extension that describes the external peering connectivity. Gluing the two together, it has the full internal topology of AS1 and the exit peers, together with the label associated to each peer and physical interface to the peer. So basically, the controller acquires all the information it needs to map the network and the external connectivity and have the necessary label to steer the traffic the way he wants. How the controller will make a traffic engineering decision is specific to the operator and it's outside the scope of the discussion. The key point to note is that as part of the inputs to drive the policy decision, you might use EPE itself to basically steer your probes to each of your transit providers, valid transit providers, to basically assess the performance through them. Finally, the final step is basically once the decision to do a traffic engineering steering is done, how to program it. There are many ways to do it. The controller could send a BGP 3107 route that would override the classic internet route with the next hop specifying the exit point and the label specifying the BGP peering segment. It could be a VPN v4 route, but an obvious way to program it is to use a PSEP programming. So that's the one I describe in this case. The other models, I explained it in the draft. So the controller would send a PSEP message to A to say, hey, please build a segment routing traffic engineering tunnel. This tunnel consists in pushing two labels. The top label is 64. This is the node segment to C. It will steer the traffic to C on the shortest path to C. The next label is 1042. This is the peer hatch segment that C allocated for the bottom link to F. And so by creating that policy and the traffic steering policy that says all the traffic from A to M/8 should go over the tunnel, when the traffic gets to A, it's routed on the tunnel, the two labels are pushed, 64 gets the traffic to C, the selected border router, the next label is 1042, so C is going to receive a packet where the top label is 1042, 1042 is popped, and the traffic is sent on the related interface to F, and so the traffic engineering decision, which was to steer the traffic from A to M/8 via C instead of the best path via B, and specifically the bottom interface to F of a transit provider blue, has been realized. Conclusion? we basically achieve the goal of allowing a traffic engineering decision on a per flow basis with the state only programmed at the entry, at the ingress border router or directly at a host where the content is sourced from. You can then steer your traffic via any border router you want and each interface to the peers you want, either at the granularity of a physical interface, a peer, or I did not explain it here, but you could also do it as a group of peers. For example, an AS or a region, a part of your neighboring peers. The way you do it is completely integrated with the intra-domain traffic engineering capability or use case within segment routing. So it's an integrated scheme with intra-domain and inter-domain. There is zero assumption on the IBGP design. So your valid internet routes, the way you distribute them for your normal classic BGP best path, you could set next stop self. That's fine, that's better from a stability viewpoint. We do not require that you preserve the next stop. We don't need it because this is conveyed via the EPE policy. And the per flow state is only installed at the source host or at the ingress border router. So that's the EPE use case, so one of the many use cases for segment routing. The point of this presentation was to attract your attention. As for any other use case, your feedback is extremely important. Have we missed any requirements? Is there any other applications that you can think of? Don't hesitate. Your contribution is really welcomed. And many thanks to the colleagues from Facebook and Yandex to help us through this use case. Many thanks. Yeah, perfect.
Any questions?
Okay.
All right, Ethan Katz-Bassett from USC, who will be presenting the peering test bed and using that for routing research.
Thanks. Thanks, everybody. So BGP and interdomain routing hasn't changed much in recent years, despite many problems that we know about it. And I believe that this is partially caused by the barriers that exist to doing meaningful BGP research. I'm going to tell you today about a test bed that we've created called peering, and it can help change the game for interdomain research by really enabling researchers to do impactful research that's hard for them to do today. I have three main reasons for coming to NANOG and talking about this. First, I want to help you all understand the test bed because we already peer with many of you, and many of you might see experiments that we're running. Also, we're interested in expanding the test bed, so I'd love to talk to people who might be willing to help us out with that. And finally, I'd like to talk to people who are interested in using it or who might have problems that they're interested in having us tackle with it because we'd like to do impactful research. Okay, there we go. So there have been enormous changes in networking in recent years. We use the internet now for streaming video and interactive applications. We run many of these applications in advanced data centers, often using software-defined networking. And the rise of mobile has changed how we interact with the internet and also brought it into places that were kind of previously remote and cut off. But all of these islands of innovation are still interconnected by BGP, and BGP has remained essentially unchanged in the 20 years since the founding of NANOG. Now, it's great that BGP has supported all of these growth and innovation in all these areas, so you might ask, why is this a problem? Well, BGP contributes to a number of known problems on the internet, and I've listed a number of them here. It's hard to get good performance out of BGP or reliable performance. There's a number of security vulnerabilities. There's nothing to prevent hijacking or route leaks. And the list goes on and on. So for the rest of the talk, I'm going to answer the question of what we need to enable impactful research in these areas. I'm going to start by discussing why we believe that one of the big roadblocks has been a lack of good tools for conducting research. After that, I'm going to talk about our peering testbed and how it solves this problem by providing the tools that we need to do the research that we'd like to do. Well, how do we do research today on interdomain routing? One way is via simulation or emulation. And the great thing about this is that you have complete control of your experiment and complete visibility into your experiment. But the experiments will only be as realistic as your ability to configure them properly. And we don't have enough knowledge about the internet's topology or about the routing policies in place to have effective simulations. The other main approach is to actually measure real routes using things like traceroute or looking glasses. And here you're seeing real routing on the internet. But you can only passively observe the choices that are being made, and you can't influence those choices or see how other ASs would react to something that you introduce. In the rest of the talk, I'm going to talk about how our testbed provides capabilities that these previous tools lacked. With our testbed, we pair an emulated experiment with real interdomain connectivity via BGP. So a researcher can emulate the AS that they like, including defining its topology and whatever policies they want it to run. We can then connect it to real ASs via BGP. And then the experimenter controls the AS and can make whatever announcements they want and exchange routes and traffic with the real internet. Much of our connectivity today is via AMSICs, who have generously been hosting us for the last year. We also have connectivity at a number of universities, but I'm going to just use AMSICs as an example. So we have an ASN allocated to us. It's 47065. We peer with hundreds of ASs at AMSICs, many via the route server. And what we can do is define some experiment. So I can run something on my laptop and then hook it up via this peering router. So what that means is that the peering router essentially acts as a multiplexer, allowing multiple experiments to run behind it. Each of these experiments will use a private AS number to establish a peering with the peering router. The multiplexer will then transparently provide them with connectivity to each of our actual peers. And then in my experiment, I can run whatever topology I want, which we emulate using an extended version of Mininet, which is an emulation environment. We can peer using, say, Quagga to establish that peering session. Once I'm running this experiment, I can advertise out prefixes as I like, including specifying which peers they go to and which ones they don't go to. The multiplexer will pass on the announcements that it receives to each of the experiments. They're then free to choose whichever routes they want and exchange traffic with the internet. And in particular, it transparently connects each experiment, so the experiments are isolated from each other and can make different routing decisions. So the last time, or I guess the first time I spoke at NANOG about BGP was here in 2007 when it was in Bellevue. I was a grad student, and at that point, I assumed that I would have no way to conduct the types of BGP experiments that I wanted. I figured people like Randy Bush had access to these resources. They could use a prefix in an ASN, and they had the ability to establish peerings, but there was really no way for me as a grad student in University of Washington to kind of conduct these types of experiments. And so I want to set up this testbed for the community to solve these problems once for everybody and enable everyone to access them. By providing this central testbed, we only have to establish these peerings once. And we can also put in place safety, for example, filters to prevent bad traffic or bad routes, hijacks, spoofing, things like that. We can also put in place rate limits on announcements and traffic. And this also allows us to centralize relationships. So other ASs only need to peer with our testbed. They don't need to know anything about the individual experiments. They just need to know that our ASN is an academic research one. And this lets us keep stable peerings that don't come and go as different experiments run. It also gives a central point of contact for operations and support. We've used the testbed already for a number of projects. I'm just going to quickly touch on them, and I'm happy to talk to anybody about them more offline. We recently built a software-defined internet exchange, which provides a clean language for specifying policy over a peering fabric and gives you more fine-grained control than you might have today. We had a project last year on tracking down the root cause of path changes. So if a path towards you changes, it can be hard to figure out what triggered that change because BGP announcements on the internet have a rippling, cascading effect, and our system lets you track down the cause. We also had a system that let you make controlled BGP announcements to route around failures. There's also been other groups that didn't include me that used the testbed, so I'd encourage you to talk to Simon Peter, who's here at NANOG this week, about his system Arrow that lets you provide remote customers with a tunneled transit as a service. And also, a few years ago at NANOG, there was a talk on joint content and network routing that used our testbed. To wrap up, interdomain routing has barely changed, despite many known problems. My position is that a central cause of that has been the difficulty in running experiments. Our testbeds intended to overcome this hurdle and enable new types of research by enabling researchers to define ASNs of their choice and then actually connect them on the internet to exchange traffic and routes. I'd love to talk more with people here. In particular, we want to do meaningful research, and you guys are the best sources of problems, so I'd love to hear from you about what problems in interdomain routing you have that you think we should look at. We're also looking to expand our testbed. So far, we've mainly been looking at internet exchanges and remote peering options just because they let us expand the testbed quickly, but I would love to talk to anyone who's interested in peering with us or hosting our testbed. I have a contact email up there, bgpmux-knock@gtnoise.net, or you can just contact me in person. I'll be around for the rest of the week. Thanks a lot. I'm happy to take questions.
Matt Petak, Yahoo. Perhaps I misunderstood, but did you actually say you want to open this up for random people to run experiments feeding prefixes out onto the global internet?
Not random people, but I do want to open it up to researchers. So we have a committee that vets experiments. We also have in place filters, so you can only make announcements for our prefixes that are under our control. We also rate limit the rate at which you can make those announcements. That keeps you from being able to hijack, leak, cause too much churn. We limit the traffic that you can send both by rate limiting it and by keeping you from spoofing. So essentially, we can only impact routes to our prefix, and you can only send and receive traffic to our prefix, and it's all at a low rate.
And the other piece was you said that researchers could pick AS numbers to use, or do you have a specific set
So we
of
have an
AS
AS number. It's 47065. Behind that, individual experiments will use private AS numbers. Those get stripped out before they're announced to the public internet. So all experiments behind our testbed look to the rest of the world like it's 47065, but we have a /19. We might subdivide that into 24s, and different experiments use different 24s.
That's much cleaner than I thought. Thank you.
Sorry for not explaining it clear. So yeah, it's entirely transparent. From the experiment's point of view, it looks like they're the only experiment running. From the rest of the internet's point of view, it looks like just 47065 making different announcements. Thanks for the questions. Sorry it wasn't clear. Any other questions? I'll be around at the socials both nights and around all day tomorrow, so I'd love to chat more with people.
All right, so we've come to the end of our programming today. Since you've had the benefit of all this programming, we'd appreciate if you could fill out the PC survey on the NANOG website to let us know what you thought. We will be back here tomorrow with an 8:30 breakfast and 9:30 start to plenary. There are 2 socials tonight, starting now at 6 o'clock downstairs at the Evergreen Ballroom is the Centrus and Spectrum Cocktail Hour. And there's a small handout, but it's just downstairs. And Facebook is hosting this NANOG social from 7 to 10 at the Bellevue Rock Bottom Brewery. This has information and a map on the back. Enjoy yourselves, and we'll see you back here tomorrow.